Measuring the quantum properties of advanced materials like colloidal quantum dots, topological insulators, and plasmonic particles requires a variety of sophisticated techniques. One common method for colloidal quantum dots is photoluminescence spectroscopy. In this technique, the quantum dots are excited by a light source and the emitted light is analyzed. The spectrum of this emission provides key insights into the electronic states and bandgap energies of the quantum dots. For example, by examining the emission peak, researchers can deduce how size and surface chemistry affect quantum confinement. How does the size of the quantum dots affect their photoluminescence? Smaller dots generally emit light at shorter wavelengths due to a larger bandgap, a phenomenon that directly demonstrates quantum confinement effects. For topological insulators, angle-resolved photoemission spectroscopy, ARP is a powerful tool. ARP involves shining ultraviolet or X-ray light on the sample to eject electrons, and then measuring the energy and momentum of these electrons. This process helps map out the electronic band structure, revealing the characteristic surface states that are protected by the material's topology. By analyzing the dispersion relations, scientists can confirm whether the surface states are robust against perturbations, a signature of topological insulators. Why is ARPES particularly effective here? It directly visualizes the energy-momentum relationship of electrons, providing a clear picture of the quantum mechanical effects that govern these materials. In the realm of plasmonic particles, techniques such as electron energy loss spectroscopy, EELS, and dark-field microscopy are commonly used. EELS is performed in a transmission electron microscope (TEM) and measures the energy lost by electrons as they interact with plasmon resonances in the sample. This technique provides high spatial resolution and can map out plasmonic excitations across individual particles. Dark-field microscopy, on the other hand, exploits scattered light to image nanoparticles and observe their localized surface plasmon resonances. What kind of information can dark-field microscopy offer? It allows researchers to monitor shifts in resonance peaks, which indicate changes in particle size, shape, or the local dielectric environment. Other complementary techniques include Raman spectroscopy and Pumper spectroscopy. Raman spectroscopy can provide vibrational fingerprints that are sensitive to the nanoscale structure and any surface modifications of quantum dots or plasmatic particles. Pumper spectroscopy, which uses 2 ultrafast laser pulses, allows scientists to study the dynamics of electron excitation and relaxation in these systems, offering insight into the transient quantum states. Each of these techniques plays a critical role in unraveling the complex quantum properties of these materials. By combining methods such as using ARPES for mapping electronic structures in topological insulators, photoluminescence spectroscopy for quantum dots, and EELS for plasmonic resonances, researchers can build a comprehensive understanding of the underlying quantum mechanics. Could these combined approaches lead to better design and optimization of next-generation devices? The answer seems promising, as understanding these quantum effects is key to advancing applications in optoelectronics, quantum computing, and nanoscale sensing. Photoluminescence spectroscopy measures the light emitted by a quantum dot after it absorbs photons, providing insights into its bandgap and quantum confinement effects. When a quantum dot is excited by a laser, electrons transition to higher energy levels and then relax, emitting photons with wavelengths characteristic of their size-dependent energy levels. PL spectroscopy helps determine quantum efficiency, excitonic interactions, and electronic transitions in colloidal quantum dots. The emitted light spectrum shifts as the dot size changes due to quantum confinement, allowing precise control of optical properties. For example, CDS quantum dots exhibit a size-dependent PL emission, shifting from blue to red as their diameter increases. It's like tuning a guitar string. Shorter strings vibrate at higher frequencies, just as smaller quantum dots emit shorter wavelength light. Ultra-fast transient absorption (TA) spectroscopy measures the dynamics of excited carriers in quantum dots, topological insulators, and plasmonic materials over femtosecond to picosecond timescales. By using a pump probe technique where a laser pulse excites electrons and a second pulse measures their evolution, This method provides insights into carrier lifetimes, energy relaxation pathways, and hot electron transfer. TA spectroscopy is crucial for studying non-equilibrium charge carrier behavior, essential for applications in quantum computing and photovoltaics. It reveals how quickly excited electrons return to their ground state and how they interact with the lattice. For example, lead halide perovskite quantum dots exhibit long-lived charge carriers, which enhance their efficiency in solar cells. It's like watching a bouncing ball in slow motion. This technique captures every tiny step of electron movement after excitation. Angle-resolved photoemission spectroscopy, ARPES, directly measures electron band structures in materials by ejecting electrons using high-energy photons and analyzing their momentum and energy. This technique is particularly useful for probing the topologically protected surface states of topological insulators, which have spin momentum locking and unique quantum properties. ARPES helps scientists visualize Dirac cone dispersion, electronic correlations, and energy momentum relationships. It provides experimental verification of topological order and quantum spin Hall effects in new materials. For example, ARPES has been used to confirm surface states in Bi2C3, a well-known topological insulator. It's like mapping ocean currents from satellite images. ARPES reveals how electrons move within a material without disturbing them. Surface-enhanced Raman spectroscopy, SR enhances the Raman scattering signal of molecules placed near plasmonic nanoparticles, amplifying weak vibrational signals by several orders of magnitude. Plasmonic particles, such as gold and silver nanostructures, create intense localized electromagnetic fields, which enhance the interaction between light and molecular vibrations. This technique enables ultra-sensitive detection of phonon modes, molecular vibrations, and charge transfer interactions in quantum dots and topological materials. It is widely used for studying quantum coherence, phonon-electron coupling, and chemical sensing. For example, gold nanostructures enhance Raman signals. In graphene, it's like using a microphone with extreme amplification. Even the faintest sound or quantum vibration becomes loud and detectable. Electron energy loss spectroscopy, EELS, measures the energy lost by electrons as they pass through a material, providing information about plasmons, excitons, and phonon interactions. This technique is highly effective for studying plasmonic nanoparticles, where collective electron oscillations influence optical properties. EELS can also resolve localized quantum states, bandgap energies, and surface plasmon resonances with nanometer scale precision. It is particularly useful for materials with low energy excitations, such as quantum dots and 2D topological insulators. For example, EELS has been used to map localized plasma resonances in silver and gold nanospheres, confirming quantum size effects. It's like listening for echoes in a canyon. The way electrons lose energy tells us about the quantum structure they travel through. Scanning tunneling microscopy, STM, allows direct imaging of electronic states at the atomic scale by measuring tunneling current between a sharp probe and the material's surface. This technique is ideal for visualizing quantum dots, topological edge states, and electronic wave functions in 2D materials. The quantum tunneling effect enables STM to measure local density of states, LDOS, and atomic scale defects, crucial for characterizing topological insulators. It provides unparalleled spatial resolution, revealing localized quantum effects in nanoscale materials. For example, STM studies on topological insulator Bi2T3 have confirmed the presence of spin-polarized edge states. It's like reading Braille with a super-sensitive finger. STM detects nanoscale bumps and electron distributions invisible to the eye. Time-resolved Kerr rotation spectroscopy uses polarized laser pulses to measure spin precession and coherence times in quantum dots and topological materials. It is especially useful for tracking spin lifetimes, quantum coherence, and spintronic properties in materials with strong spin-orbit coupling. Kerr rotation is crucial for understanding spin-based quantum information processing and non-equilibrium spin dynamics. The technique provides time-resolved insights into how long quantum spin states remain stable before decoherence occurs. For example, topological insulators like HGTE exhibit long spin coherence times, useful for spintronic applications. It's like watching a spinning top slow down in ultra-slow motion, measuring how long it remains stable before falling. X-ray absorption spectroscopy (XAs) examines how X-rays interact with inner shell electrons, revealing information about oxidation states, bonding environments, and electronic hybridization in quantum materials. This technique is crucial for studying dopant effects, charge transfer, and orbital interactions in colloidal quantum dots and topological systems. By measuring absorption edges, researchers can determine element-specific electronic structures and fine-tune material properties. XAS is particularly valuable for understanding how quantum confinement influences electronic configurations. For example, XAS studies on lead sulfide quantum dots have provided detailed insights into their electronic hybridization. It's like using an X-ray scanner to analyze the internal composition of a gemstone without cutting it open. Quantum noise spectroscopy measures random fluctuations in quantum systems, providing insights into decoherence mechanisms in quantum dots and topological materials. By analyzing noise signatures, scientists can identify sources of quantum instability, environmental interactions, and coherence-breaking events. This technique is particularly useful for improving quantum computing materials and noise-resistant quantum states. It helps refine materials with longer coherence times for quantum memory and sensors. For example, silicon quantum dots have been optimized for longer coherence times using quantum noise suppression techniques. It's like identifying weak radio signals in a noisy environment, helping to isolate the pure quantum signal